Welcome to Jackass Economics Edition. Oh god. Green screen, I choose you! Hello! Again. I look like a small man. Do we have a guest? Oh, we have a guest! We have a guest for the show! It's a little boy! It's a little boy! Hey! This is the third time I'm trying to record this video, and hopefully it goes better this time than the last two times. The reason I've had to do it so many times is because I feel like with this particular material, if I screw it up, it's just a really bad thing for everyone. I don't want to put you guys through what I had to go through when I was learning this material, because explaining algebra can be difficult for many people, and I did not have very good algebra teachers growing up. So I just want to make sure this is as clear as possible, and here I am. I think I've got everything ready. I've got a template this time and a script instead of just trying to go in, what's the word? Blind. This is the second episode of Video Game Economics, and this episode is on the exciting topic of algebra, and actually not really so much algebra, more so returns to scale, but I'm going to be using returns to scale to explain the use of algebra in economics and how powerful it can be. And for me, when I was going through high school and some of college when I was learning algebra, it was just like, this is so useless, this is so stupid, why would anyone ever use this? And then as soon as I got into econ, I realized, oh, hold on a second, it actually is useful. The thing is, they just don't tell you that, which, gotta love education, right? So hopefully I can give you a new lease on life with this algebra, and you can see just how exciting math can be if it's used correctly. So let me just go ahead and go over to my OneNote, and we'll kick things off there. We in it, boys! Look, it's me, I'm in the OneNote. How cool is that? So, returns to scale. We talked a little bit about returns to scale in the first episode when I was talking about how the demand curve works and how it incorporates diminishing marginal returns to scale. And remember what I said about that is, for example, if you have many shooters and few RPGs, you'll want to buy more RPGs because you get more marginal utility out of it. Because you already have so many shooters, why would you want another shooter? You could just get another RPG and you get so much more out of it. That's the basic idea of it. So now I'm going to be kind of explaining it more algebraically, and I'm going to try and give some kind of video game-esque examples to try and get you guys to understand how diminishing marginal returns works, as well as the two other types of marginal returns, which are constant and increasing. Now, constant and increasing, they're a little weird because they're just not too common in real life. And the reason is because most things are diminishing. Your utility from something, the more you have of it, tends to diminish, just in most things in life. But I tried to come up with some good examples of situations in video games and having to do with video games that would exhibit these constant and increasing returns to scale, and I hope they're good enough, because it was pretty tough to come up with them, but I had some good help on them, and I'll get to that part. But let's just go ahead and start talking about kind of the algebraic background of returns to scale. You might be looking at this right now and saying to yourself, I have no idea what I'm looking at, and I'm going to explain everything, so that's the cool thing. So here we have diminishing marginal returns to scale, and what we have right here is what it would kind of look like. Something usually with a square root, and I'll show why that is in a second. But let me just kind of give you my example here. So say you're playing Pokemon, and you have no Pokemon, so clearly you're winning no battles. So let's say that because of that, your input is Pokemon, and I'll explain why, but let's just say it's water-type Pokemon. So we'll put on the x-axis, these numbers on the x-axis are always going to be your x input, or your input. And then on the y here, let's say it's battles 1, and we'll call that b. And because of that, I'm just going to change some of these variables in this equation I have here. So instead of being f of x equals square root of x, it'll just be f of w equals square root of w. And we're just talking about water-type Pokemon there. So I have all these things here, and it's x equals 4, x equals 8, x equals 16, x equals 24. We'll call this the amount of water-type moves you can do. Let's go ahead and put that as w. So really what I'm saying for the x-axis here isn't water-type Pokemon necessarily, but more just water-type moves you can use. And so if you know anything about Pokemon, you know that you want to try to diverse the kinds of moves you can do. Because if you have all water type moves, then, you know, marginally the amount of water type moves you'll have become more and more useless. If you already have a handful of good water type moves, you don't need more. And so I'll explain how that works economically. We're looking at this kind of equation here, f of w equals square root of w, and then these w equals is our water type moves. Let's just look at this. I'm gonna go ahead and label these real quick, and then over here on the side we're just gonna go regular normal. Here on our x-axis we have water type Pokemon moves that we can use, water type moves. Over here we have battles won, right? And I kind of spread it out more because that's just how the kind of math works here. What's more important is what the line looks like. And so we're just going to do some quick math here. So when I say w equals 4, w equals 8, w equals 16, w equals 24, this is kind of a hypothetical saying, well, what if I had 4 water type moves? How many battles would I win? What if we had 8 water type moves? How many battles would I win? 16, 24, and so on. And again, these are kind of approximations. We're creating a function based on kind of a hypothetical situation where our marginal returns from getting more Pokemon is this function right here, f of w equals w. And remember, you can say f of w is basically the same as b, which is our output. So let's say b equals f of w, which equals square root of w. With that in mind, let's go ahead and do the math here. So the first point here is w equals 4. Square root of 4 equals 2. So, on point 4 here, we're looking at 2. So immediately we have this line right here. W equals 8, let's see what the square root of 8 is then. Square root of 8, 2.82. So that might be somewhere right there. 16. 16, square root of 16 is 4. And see, we're doubling our outputs. We've got this, 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 and then 24. Let's just see what we get. Square root of 24, 4.89. So, you know, that's going a little bit off of here, but let's just say 4.89 is like right there. And so you see how this line looks. It's concave. It immediately starts going up pretty rapidly, but then quickly diminishes. And so that's why it's diminishing marginal returns. So I hope that makes sense. So let me just explain one more time how inputs and outputs work. So this equation we have is f of w equals w, square root of w. So what that basically means is that our input is w, and so along this axis we're going to solve for whatever we're looking for whatever point. So the first one was 4. So we got 4, square root of 4 is 2, and that's our output, which is b. But b is also a function of w. So this function of w here is basically the same thing as this b here. So that's what diminishing returns to scale is. Basically, you double your inputs, you get less than double your outputs. You triple your inputs, you get less than triple your outputs because it's diminishing. And you can see how that works mathematically here on this line. And so let me do a couple more examples. Hopefully that part makes a little more sense. We're going to talk about constant returns to scale now. So for constant returns to scale, the example that I came up with is you're playing Last of Us and you're getting gun upgrades. If you've ever played The Last of Us, you know that scraps are how you get upgrades for your guns. You scrap items from around the world, like scissors and tape and all that kind of stuff. So that'll be our input. So we'll call that S for scraps. And then for our output, we'll put damage for the amount of damage you get from that upgrade from your gun when you use the scraps to upgrade your gun. So on this axis, we'll call it D. And so I'm going to do the same thing with this one. We're going to change this a little bit. So instead of being f of x, it's going to be f of, what was it? S for scraps. So function of scraps is 2s. So 2 times the scraps there. So let me just change these real quick. So think about it this way. You're putting your scraps in, and what are you getting out of that? You're changing your scraps into gun upgrades. What's the damage? What's your output? And so, here again, f of s is basically equal to d because d is your output. It's on the y-axis. So let's solve for each one of these. S equals 1, easy stuff. I don't even have to use the calculator for this, right? Easy stuff. All you do is plug it in for the S there. So S of 1 is just simply, there's 1 down here, I'll go ahead and label that. It's just 1 times 2. So there you go. S of 2, 2 times 2 is 4. Easy enough. S equals 4. 4 times 2 is 8. And 8 is 16, but that's not on this on this graph because I didn't have the foresight. But you know, you can imagine where it is. It's probably somewhere up in this region right here. But what you can do is look at this, and I'll connect these dots, and you'll see it would be a straight line, and that's because it's constant. So that's what constant returns to scale is. Basically, you double your inputs, you get double the outputs. You triple your inputs, you get triple the outputs. So on and so forth. Now we're going to talk about increasing marginal returns to scale. So this one's the really weird one, and the one that I had a hard time coming up with an example for, but I had my resident civilization expert, Nick, to help me come up with an example for this one, and I think Nick did a good job, so thanks, Nick. We're gonna look at this, and the example that Nick gave me is you're playing civilization, and with catapults, with each catapult that you get an increasing marginal tactical advantage. So when you're playing Civ, you have 1 catapult, you've got some pretty good tactical advantage. You get 2, you get more than double the tactical advantage. You get 3, you've got more than triple the tactical advantage. That's because they're just so overpowered in the game. So let's say on the x-axis, when we're talking about civilization, we'll put C for catapults because that's our input. And our output then would just be tactical advantage. We'll just put that as a T. And obviously that's a little bit more abstract, but just try and, you know, this is a lot of economics, is thinking abstractly about things and applying a number value to them. So we're going to be applying a number value to tactical advantage. So, like I said, with the last couple ones, we're going to kind of rewrite this equation so that it makes sense in this context. And so we're looking at catapults. So f of c, then, equals c squared. And I'll change all these to c. This one we're going to have to kind of divvy up a little bit differently because, again, what's important is what the line looks like, not so much the numbers. So I'm going to just do it by this. Let's do it like this. We're going to go ahead and do the math here a little bit. So remember, you just plug in your x onto this c here. And we'll go ahead and label these just normally. So we're going to go ahead and plug in each of our c values here into the equation and see what our output is. And you know, just to reiterate one more time, this f of c is basically t, because they both signify our output. T and f of c are the same. So 1 squared, easy enough, is 1. So 1 would probably be down like right here. So 1, 1. 2 squared is 4. So let's say 4 is probably right around there. Again, this is kind of an estimation. What's important is what the line looks like. We're going to go ahead and go over to 4. 4 squared is 16. So we're going to go ahead and go right up here. That's about where 16 would be. And we're going to kind of jump quite a bit. And when it comes to exponents, one small change in input could have a huge change in output. So we're just going to go straight to 8, and we're going to see what this line looks like. 8 squared is 64. So 8 and 64 is right about, say, right here. And so let's go ahead and connect these dots to the best of my ability. And so you look at this and you see it's a convex line. The line is going up like this at an exponential rate. And you know, again, I'm a little shaky, my handwriting isn't great, but you can see how that works. So basically what we're looking at here is you double your inputs, you get more than double your outputs. You triple your inputs, you get more than triple your outputs, and so on because your marginal returns are increasing. So there you go. That's marginal returns. I'm going to have to save supply and demand for the next episode, or maybe I'll do like a little short episode, something just in between, but it looks like we're out of time for today, so thank you for watching. I hope this was informative, and you have yourself a dang old day. I don't know how to end videos.